talked about acids and bases. And by the way, I don't know why these have these beautiful, colors, but, well, purple is beautiful. Acids and bases. And we said an acid is really something that is a proton donor, gives off protons, and the base is a proton acceptor. So I gave you the example of, say, HCl in water, which would react to H plus Cl minus. So HCl obviously very clearly is the acid. It gives off the protons. So this is the acid, and this would be the associated base. This would be the conjugated base. And that is a conjugated acid-base pair, because they are related to each other. And I told you that in a conjugated acid-base pair, the only difference between the acid and the base is that the acid has the additional proton. We also discussed the pH. So we had pH, and we defined that pH is the negative logarithm of the proton concentration. And we always have to use the proton concentration in mole per liter. Okay? I think this is where we predominantly stopped then last week. So let's do, what do we do? Let's do a little example. And I told you what would happen if we have, say, 0.1 molar hydrochloric acid. Can we calculate the pH? pH equals minus log of, and we assume that the hydrochloric acid completely dissociates. So what we would get in this case, we would get a 0.1 mole per liter protons and 0.1 mole per liter chloride ions. And here's our proton concentration. So all we need to do is minus log 0.1, because we already have it in the right unit as mole per liter, and this would give us, bless you, this would give us what? pH? pH equals 1. Log 0.1 gives minus 1, and minus times minus gives plus, so we've got log a pH of 1. Excellent. Now, in this case, we are dealing with something that completely dissociates. But sometimes life isn't that easy. We might encounter substances that don't completely dissociate. And one of these substances is, for example, water. So water would dissociate into what? A proton plus a hydroxide ion. Okay? But it doesn't do that all the time. And in fact, only 1 in 10 million water molecules actually does that. So 1 in 10 million. So that's the same as 1 over 10, 100,000, 10,000, 100,000, 1 million, 10 million. Yeah? Only one of these 10 million molecules will do this reaction proton into OH minus. So if I have water here, what is the proton concentration? If I've got a pot of pure water, what is the proton concentration? Hello, good morning. What do you reckon? Let's say I have 1 mole of water. So 1 mole of water. How many grams is 1 mole of water? $18 grams, yes, you're absolutely right. So 1 mole is, because the molecular mass of water is 18 gram per mole. How do I know that? Well, hydrogen is 1, oxygen is 16 in the periodic table. So 2 times 1 plus 16 gives us 18 grams per mole. Let's say I have 1 mole of water and only 1 in 10,000 molecules actually, 10 million molecules actually dissociate. How many moles of H plus do I have? 1 in 10 million. So that would be 1 times 10 to the minus 7 mole. Yeah, because it's 1 in 10 million. Here is a question for you guys. Let's see if you can do that. What is the concentration of water? Has he completely lost his marbles? What is the concentration of water? Do you want to quickly try it out yourself and then convince the person sitting next to you that your answer is right? Or you admit defeat and say, I don't have a clue how to do that. Time now. Try to figure it out. What is the concentration of water? All right? No? Not all right? Okay. What is the concentration of water? Got it? No? It sounds like a bizarre question, doesn't it? You're absolutely right. Okay. Did you get an answer? What do we know about water? We know the molecular mass. Which is 18 gram per mole. We also, okay, so the question was about the concentration of water. What is the unit of concentration? Yeah, you loud? Molar, or I can write it as mole per liter. Mole per liter. Let's do that with dimensional analysis. Do we have mole anywhere? Yeah, so we write it as mole and 18 grams. Okay? Now the mole is good, but we need to get rid of the grams. And we need to find a relationship where we have grams and liters in it. Can we find that? How many grams are in 1 liter of water? 1,000. So we have 1,000 grams, because 1 liter weighs 1 kilogram, which is 1,000 grams. So we want to get rid of the grams, so we have 1,000 gram in 1 liter. What happens to the grams? Hasta la vista. What we have left is 1,000 mole divided by 18, and the unit is liter. So what's 1,000 divided by 18? 55.56. What's the unit? Mole per liter, which is the same as 55.56 molar. So if you have water, plain unadulterated water, which you shouldn't drink, you know why you shouldn't drink water? Just in case you don't know, but fish have sex in it. Yeah, it's true. Water has a concentration of 55.5 molar. Okay? So, coming back to our problem, if we have water, if we have 1 mole of water, we have 1 times 10 to the minus 7 mole per liter of protons. So our concentration of protons is 1 times 10 to the minus 7 molar. Can you tell me from this, what is the pH of water? Loud? 7. Why? You're right. So all we need to do is minus log of 1 times 10 to the minus 7. This here gives minus 7 times minus, so the pH is 7. pH of pure water is 7. Simply because we have this concentration of protons in water. So, we have our equation. H2O gives us H plus OH minus. And we said that this is 1 times 10 to the minus 7 molar. What is the concentration of the hydroxide ions in water, in pure water? Loud? It's the same, exactly, because for each proton that we get, we also get one hydroxide ion. So that would be 1 times 10 to the minus 7 molar. Yeah? That makes sense. Now we can define something else. We've defined the pH. Well, we could also define a pOH. How would you define a pOH? Loud? Absolutely. It's the minus log of the hydroxide ion concentration. So, what is the pOH of pure water? So the pOH of pure water is also 7. That make sense? Yeah? Now, what you can do is actually something quite funny. Well, at least a chemist would see the funny point of that. What you can do is you can actually add up pH plus pOH. Gives you 14. And I want you to remember this 14. This is actually sort of a magic number. Whatever solution you use, whether you have an acid or a base, but in pure water, with this solution in it, pH and pOH will always add up to 14. Yeah? So let me give you an example. Let's say we have a 0.01 molar hydrochloric acid solution. Can you give me the pH and the pOH of this solution? You can do it together if you like. Got it? It's pretty straightforward, isn't it? pH is 2. Simply minus log of 0.01. That's the proton concentration. Log of 0.01 gives us minus 2 times minus gives plus 2. And the pOH we can calculate from the fact that pOH is 14 minus pH, bless you, equals 12. What does that actually mean? What does this, if we sort of think about that, what does this tell us? What is our concentration of protons in the solution? So the concentration of protons is 1 times 10 to the minus 2 mole per liter. Yeah? What is the concentration of OH minus? Thank you. 1 times 10 to the minus 12 mole per liter. So that's tiny, 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 wincy tiny. Please don't write that in an exam or something like that. It's just very, very small. And the funny thing is, what do you get when you multiply the H plus concentration, you multiply that with the OH minus concentration? Try that out. What do you get? Loud? 10 times 1 times 10 to the minus 14. What's the unit? What's the unit? Mole per liters. Ah, yes, I heard it. It would be moles squared, liters squared, isn't it? Because we have the unit mole per liter here and mole per liter here. Yeah? So it would be, I can also write this as 1 times 10 to the minus 14 molar squared. Or I could define another P thingy. pH, POH. And in this case, I call this pKw. And that would be just simply 14. pKw stands for what is called the autoionization constant of water. I just got a complaint from my son because we are not allowed to say at home water. He gets told off when he says that. And he just told me off. So this pKw is 14, and that is also where this magic number of this 14 comes from. When we have pH plus POH is always 14. You don't really need to remember all the water stuff, really. The important thing that I want you to remember is that pH plus POH equals 14. So, let's do a little example. Oh yeah, I have 1 millimolar solution of sodium hydroxide, of NaOH. What's the pH? What's the POH? On your bike, on your calculator. Try to figure it out yourself. Done? So what do you get? So you say pOH is 3 and pH is 11. The other way around? So pH is 3 and pOH is 11. Who is right? You are? Okay, good. I like your self-confidence. So hands up, who got pH 11? Hands up. Who got pH 3? Hands up. It's interesting. It's not a 50-50 split. Let's have a look. What happens if we put NaOH into water? What do we get? Na plus plus OH minus. Aha. So we have a 1 millimolar solution. And let's assume that it completely dissociates. So what do we get? How many sodium ions do we get? 1 millimolar. How many hydroxide? The same, 1 millimolar, or 1 times 10 to the minus 3 molar. Yeah? Now, what do I do in terms of, can I get the pH directly from this? No, but what can I get? The pOH. pOH equals minus log of the OH minus. What's that? That is minus log of 1 times 10 to the minus 3. This gives me minus 3 times minus, so the pOH equals 3. Goes to you, the point. And what's the pH? pH equals 14 minus the pOH, and therefore it is 11. I'm terribly sorry. I like your approach. I like people who are confident. It's a little bit like me. Frequently wrong, but never in doubt. Right? Does that make sense, this calculation to you? Here's another one, and I just need to remind you of something. We said on a pH scale, usually it goes from 0 to 14, with 7 being neutral, that's the pH of unadulterated water. This range is alkaline or basic. And this range is acidic. Just to remind us of that. When you measure the pH of tap water, is it 7? No? Why not? There are lots of different things in it. So, for example, in the southeast, where we are, water that is harvested from the ground, from groundwater, is usually alkaline because there's a lot of limestone in it, which makes it more basic. In the north of Scotland, for example, where your soil structure is completely different, where you have granite, this makes the water more acidic. So you hardly ever will get tap water exactly pH 7. pH 7 is only if it is highly purified water without anything in it. Here's another question. Let's say I change the pH from 2 to 1. So on my pH scale, I go from 2 to 1. What is the change in the proton concentration? How much does the proton concentration change? What do you reckon? What's the factor? 10 times. Change is 10 times. Why? Why is it 10? You're absolutely right. Yeah? Aha. So, we would have, the proton concentration here would be 1 times 10 to the minus 2 molar. And here it would be 1 times 10 to the minus 1 molar. Yeah? This is what the pH does. So how often do you have to multiply 10 times 1 times 10 to the minus 1 to get to this one? The answer is 10 times. So a change of 1 unit on the pH scale actually changes your proton concentration by a factor of 10. In the human body, a change of factor 5 in the proton concentration usually is lethal. So you have to have in your human body the pH or the proton concentration really tightly regulated. And how this is done we will discuss in another lecture. Now, bear the scale in mind. I now give you another example, which I give you 2 minutes to discuss. What is the pH of a 1 nanomolar hydrochloride solution? pH and the pOH. Okay, over to you on your calculators. Simple, isn't it? What is the pH and the pOH of a 1 nanomolar hydrochloride solution? Got it? Got it? Yeah? Got it? Sorry? Got it? Yeah? So what's the pH? What did you get for the pH? Loud? 9. Okay. Who's got 9 for the pH? Excellent. Fantastic. You're really good. Who hasn't got something else? Who has got something else? No? So it must be true. But wait a moment. What is HCl? What is that as a substance? Say again? Say the last word? Acid. Where would you expect an acid to be on the pH scale? Between 0 and 7, right? And you just gave me 9. Do you see my dilemma? You are all lying to me. You are trying to sell me that if I put an acid into water, it becomes a pH of 9, which is alkaline. Do you see the dilemma that I have? So, Anton said, it doesn't feel right. It's a little bit like shopping or something like that. If something looks too good to be true, it's usually too good to be true. It doesn't feel right. But where did we make the mistake?
Is it because the calculation doesn't work for certain concentrations below?
You are getting there. You are getting there. Okay, let's quickly calculate. We still have a 1 nanomolar concentration of hydrochloric acid, HCl. What is our proton concentration? Our proton concentration is 1 nanomole per liter equals 1 times, what's nano? 10 times 10 to the minus 9 mole per liter. Okay, so that's a given. We can't escape this fact. We put that into water, obviously. It's a watery solution. What is the proton concentration in water? Loud? 1 times 10 1 times 10 to the minus 7 mole per liter. Bless you. Yeah? That is what water brings in terms of protons. So we add 1 times 10 to the minus 9 mole per liter from the acid to 1 times 10 to the minus 7 mole per liter protons from the water. So what is our total proton concentration? So the sum of the protons equals 1 times 10 to the minus 7 mole per liter plus 1 times 10 to the minus 9 mole per liter. Yeah? Does that make sense? And that would give us 1.01 times what? 10 to the minus 7 mole per liter. Yeah? So let me quickly write that. So we've got a 1.01 times 10 to the minus 7 molar solution of protons. Can you do the pH of that? What is it? So the pH here would be 6.995 something. Yeah? Have we rescued our model? pH 6.995 is just a smidgen below 7. Below 7 means acidic. So this stuff is acidic. Hallelujah. But just about. Yeah? pOH, of course, in this case would be 7.005. Yeah? Whew. Saved. So when you are dealing with very, very, very weak acids or bases, or I should say dilute solutions, with very dilute solutions, you must include the proton concentration from the water. Does that make sense? Because otherwise you fall into this lovely trap where you then think, no, it doesn't look right. It's, you know, inwardly there's something, the bristles go up. And you think, can't be. Are you happy with that? I bet you, yeah? At what point? That's a very good question. You can figure that out yourself. Let's say you have a 1 micromolar solution of HCl. Yeah? So here you have 1 times 10 to the minus, what is micro? Minus 6 molar protons from the acid, and 1 times 10 to the minus 7 molar from the water. Yeah? Now add them up. What do you get? 1 times 1.1, sorry, 1.1, you're right. 1.1 times 10 to the minus 6. Yeah? What do you get when you do the pH of that? 5.95. So if we are in the range of micro, yeah, what would you get if you didn't add the 1 times 10 to the minus 7? 6. So that would be compared to 6. So in the range of micro, you already have a slight error in it. 6 compared to 5.95. Yeah? Nano, this is where it's going to bite. Make sense? Any questions? Are you happy with that? I bet you anything. Try that out with your demonstrators in the next practical class. Ask them what is the pH of a 1 nanomolar hydrochloric solution. Let's see if they can do that. And I had some interesting discussions even with colleagues, not necessarily from the university here, but from another university up north, who were absolutely convinced that a 1 nanomolar hydrochloric solution gives you a pH of 9. And oh boy, did I have a whale of a time to convince them that that wasn't right. But it was fun. Okay, can I please have the sign-in sheets? And have a good weekend, and I shall see you on Monday.